So before we talk about combustion efficiency testing, I wanted to explain the combustion process. The combustion of any hydrocarbon, pretty much any home heating fuel or multifamily building heating fuel, is based up of hydrogen and carbon. So we're going to be testing the results of what happens after we combine it with oxygen and create a spark and get ourselves a nice big flame. So we want to see what byproducts are left over to see how efficient that process was. I have a little example for you, so I want you to put on your safety glasses. Nice. And I will put on mine as well. Now, to do the demonstration, I have a oxyacetylene tank. So I have our fuel, which is acetylene, and I have oxygen as well. Now, when I light this, I'm only going to light the fuel first. The fuel is going to burn with the ambient oxygen inside the air, and we're going to get a really sooty, dirty fuel, really indicative of incomplete combustion. Then once I start adding the oxygen, we're really going to see that flame start to turn blue and get really hot, and you're going to get a much, much better combustion of that actual acetylene gas. So I'm going to light up the acetylene first. So you see the flame. It's a real orange flame. And if you look at the top, you see a lot of the black soot that's forming up here. Yep. So because we're not getting enough ambient oxygen inside this flame to be able to burn completely.
And just like in a multifamily building, sometimes on the top, you see that big puff of black
soot.
smoke.
Yeah, right. It could be from incomplete combustion that's happening inside a big boiler. So in this case, now I'm going to start to add the oxygen in very slowly. And as I add it in, you're going to start to see the flame take shape. And it's going to get a lot hotter and it's going to get a lot cleaner.
So same amount of fuel.
Same amount of fuel, but now we're adding more oxygen into the process. As we add it in, we're going to get a hot, tighter flame. And this way now, there's not that soot that's flying around it. Right. You get a much better burn of the actual fuel. So this is what we're trying to see. If we had an analyzer on this, we can see the byproducts of this combustion process here, and we can see that it's actually working really well. Hypothetically, if we had a flue pipe and this was connected to a flue system, we could actually test it and we can see what's going on and how well it's burning.
Right. And this is exactly what's going on inside of any kind of burner.
That's correct. Yep.
Okay.
Cool. Shut her down. And as we go back and we let the oxygen away, we start to get that dirty fuel again, that burning combustion. It's incomplete combustion. So you get a lot of carbon monoxide being produced as well inside here. Here we have a combustion analyzer, and all of them are pretty much the same. They're all just sampling the flue gases. We're just seeing what's left over, and most of them have 2 sensors built into them. And if I take the back off here, I can show you guys. So in the back of the analyzer, we have 2 sensors. We have an oxygen and we have a carbon monoxide sensor. So what we're doing, we're going to measure the amount of oxygen left over inside the combustion gases. So whatever going up the flue pipe, we'll measure the oxygen. There's an algorithm built into this analyzer. And once we have the oxygen number that's left over, we can calculate the rest. We can calculate the carbon dioxide content. We can calculate the carbon monoxide. And by the temperature of the flue gases, we can see how efficient we were. The analyzer, we have a little probe that's going to be connected to it. So we have the little probe at the ends, and at the end of this probe there's an opening. And what happens is there's a vacuum that's being pulled through here. So we're actually going to, these little openings on the side, pull the combustion gases through from all directions. So that's also going to measure the temperature of the flue gases as it goes through to be able to do the efficiency calculation. This all gets connected into a hose system, which these hoses go through a little filter at the bottom. Just in case you have any moisture or condensation, you don't want to make sure that doesn't get inside of the analyzer. So this little filter is there designed to stop it, to block it, to collect the condensation at the bottom, to make sure it doesn't get into the analyzer and damage all the electronics on the inside. We have a larger diameter and a smaller diameter. The larger diameter tubing is actually for the vacuum side of the system, and that's going to sample the byproducts. The smaller diameter one is the pressure gauge for our manometer, and that we'll be able to test our draft with. And we have 2 temperature ports on the inside. We have one for stack temperature and one for ambient air temperature. So this is going to be in the stack, so we want to put it on the stack side. So that goes right inside here and gets pushed in. So now that can measure the temperature of the flue gases in the stack. The air setting, this one is going to be used when we have sealed combustion units. When we have a unit that's actually pulling its combustion air from the outside. So we want to measure whatever the combustion air is coming from, we want to make sure that we sample that temperature, because the analyzer, what it's doing to get stack temperature, it gets a net reading. So it's not the actual flue temperature inside the actual flue pipe, it's actually that minus the ambient room temperature. When we have sealed combustion units, that air is coming from the outside. So can't just sample the ambient air room inside the boiler room. We need to figure out where the temperature is coming from. So we would put this into the air setting on the sealed combustion boiler, and this way now we can get the true net stack temperature of the system. You fire up the analyzer, it's going to go through a calibration process for about 60 seconds. What it's doing is it's actually turning the vacuum on and it's pulling air through the probe. It's calibrating its sensors. We should really be doing this outside in a well-ventilated space, just in case we have any carbon monoxide or carbon CO2 inside this room. We don't want this analyzer to make that reading the baseline. So after the 60 seconds are up, we will be presented with a menu to be able to select our fuel type. We can test the unit that's natural gas burning, or number 2 oil, number 4, number 6, propane, kerosene. For today's demonstration, we are going to do testing natural gas. So we're going to select natural gas fuel, and at the top of the screen, it says that we have natural gas select. It imports the correct algorithm to get the correct efficiency readings out of it. On the menu, we have a few different readings that we're going to be able to calculate. The first one is oxygen, so it's going to measure the amount of leftover oxygen in the air. Right now, as it's running, it's saying it's 20.9. Stack temperature is 61, because we're 61 degrees inside this room right now. The air is around 61 degrees as well. So the air inside the room, which is going to subtract from the stack to get the net stack temperature, is 61 degrees, which is correct. Excess air is also something that's going to be calculated as well. Excess air is extra air that's added to the combustion process. Now, the downside of extra air is that there's nitrogen inside that air, which is all around us, right? 21% oxygen and 79% nitrogen for the most part. That nitrogen doesn't do anything inside of the combustion process. The nitrogen, it just goes along for the ride. It doesn't react with the hydrogen or the carbon, right? It just goes along. And what happens is it actually steals heat from the flue gases. So the more extra air we bring in here into the combustion process, the more nitrogen we bring in, the hotter our stack temperature is going to be. Now, the hotter the stack temperature is, the less efficient our boiler is.
The nitrogen actually takes
stealing
the heat along with it?
It's stealing the heat from the heat exchanger, so now the heat exchanger can't exchange that heat to the air or to the water, whatever it may be. And it also speeds up the draft. So the more air we bring in, the more air we have to get out of that burner.
So it's a balance. This really has to be adjusted correctly.
So that's why we need to use an analyzer and make sure that we have the correct amount of oxygen and carbon dioxide. When we go to do the test, we're going to need a couple other tools as well, a few other things. You do need to drill a hole in the flue pipe. If it's an atmospheric vented system where we have a single wall flue pipe, we can drill a hole inside there and to be want to test.
And do you have to plug it up afterwards?
Yep. Afterwards, we use a UL approved metal tape. And this way that can be plugged up afterwards. If it's B-vent, you want to drill into. If it's PVC or stainless steel, you don't want to drill into it. But if it's a single wall galvanized pipe that's used on an atmospheric system, we can go ahead and make our hole and do our testing, and we'll be okay. Well, the first thing we want to do is we need to identify what type of system we have in terms of the venting categories. There's 4 different venting categories, 1, 2, 3, and 4. But they're designed to explain what's happening inside the flue pipe. So their category 1 will be negative pressure inside the flue pipe and non-condensing. Non-condensing means that the flue gases inside the flue pipe are not turning back to water. At least they're not supposed to. Some systems are designed to condense all that extra latent heat out of the flue gases and turn it into water. But the venting material needs to be able to handle that. So it needs to be something that's not going to corrode because the flue byproducts are slightly acidic, and over time they will rust out and corrode the venting material if it's not designed to work with that type of condensate. Right. So category 1, negative pressure, non-condensing. Category 2 is negative pressure, condensing. Category 3 is positive pressure, non-condensing. And category 4 is positive pressure, condensing. So the first thing we need to do is to identify that, figure out which unit we're working with, and that's going to constitute where we test. All right, so here's some basic furnace anatomy. We have a typical warm air furnace. We have our return side, which is going to bring it back to the return from the apartment or from the home. That's coming down and being ducted into the side of the furnace. There's a blower motor at the bottom that's actually going to spin and cause that negative pressure inside the return pipe, and then it's going to push positive pressure through our supply. So coming off the top of the furnace, we have a supply transition, which transitions to our air conditioning coil, which then transitions to our supply ductwork. And that'll go off into the conditioned spaces and help, heat or cool the home or the apartment.
And this does both?
This does both. This system is, set up to do AC and heating. So this furnace is category 1, the venting category. So it's considered negative pressure in the flue pipe and it's non-condensing. The thing that's a little different about this one is that it's induced draft. So inside the outlet of the heat exchanger, we have this little inducer motor.
So it's a mechanical assist?
It's a fan assisted, right. It's a draft assisted motor. So what it's going to do is when the system starts up and there's a call for heat, this motor kicks on and starts to pull negative pressure inside the heat exchanger. Now, the reason we have this motor in here is that the heat exchanger design, instead of being just straight up, it's more of a serpentine S shape. And this way we get more heat transfer. So we'll increase our efficiency, let's say from a low 70s or a mid 70s to the mid 80s. So this fan kicks in and there's two pressure switches. This system is a little more complicated in the sense that it's actually two stages. There's two firing rates on this, a high and a low. So you have two pressure switches to sense that. So the flow rate through the heat exchanger is going to be different on high and low. So it's going to be slower on low and it's going to be faster on high. So these switches are actually set up to prove that there actually is no blockage in the heat exchanger. So this fan kicks in, the pressure switches prove that there's actually no blockage, we have good flow through the heat exchanger, and that'll start the ignition sequence. So then the system will start to turn on the hot service igniter. So with different ignition systems right now, to ignite our gas, ignite our air to fuel mixture, we have a hot service igniter. So we don't have a pilot, we don't have a spark igniter, we have something that's not going to waste fuel. We won't have that pilot burning gas 24/7. This comes on only when it's needed. So this little igniter right in the back here turns on, and then the gas valve will allow the full flow of gas to come in through these burners and light all the burners up. Now, being that we don't have a pilot, we need to prove that we have a flame. So on the last burner, we have this little flame sensing rod. And what this does is that it ensures that all the burners are lit. So every burner lights up, and if this burner senses flame, then it knows that every single other one lit up before it, and it's safe to keep the furnace on. If this one doesn't sense heat, the flame sensing rod doesn't sense heat in the last burner, it shuts the system off. And then it goes through a retry. And it'll try a couple times, and then it'll go into lockout, and it won't run the system anymore because something happened. So when we test this, there's no room for dilution air to come in. The only air that comes in through the process, the combustion process, is right here at the burners. So air is being drawn in because this fan is running. We have negative pressure here, and it's drawn in. It's able to mix with the gas that's coming out of these jets. As it goes through the heat exchanger, it burns, and it works its way out through the heat exchanger into our flue pipe. So in this system, we don't have to worry about where we're going to test. We're just going to test right on the flue pipe. We don't have to look for any dilution air. So here we have an example of a Category 1 natural draft boiler. The difference between this one and the induced draft we saw before is that this one has dilution air. So on this system, we have a little draft box that comes in here, allows room air, ambient air to come in, mix with the flue gases and help assist the draft. There's no fan to help. So this heat exchanger, as you can see, is a real simple design. The burners are here on the bottom. These burners actually have a little air adjustment on them, so we can adjust the amount of air that goes into the combustion process. So if we do need to change the process and we have, a poor combustion, we can add or remove air with these primary air dampers. The flame burns, it goes straight up to the top, heats up this cast iron, it gets collected, and then it works its way out through the flue piping.
And so this one's hot water?
This one's hot water. This is a boiler system, right? So we have hot water inside here. We can either use this to circulate hot water, or this will actually produce steam as well. If you want to set it up to a steam system, you can do both. The difference is on this, when we test, we have dilution air coming in right through here. So we need to make sure we test before the air gets diluted. So when we do our combustion efficiency test and we have our probe, we can't drill a hole in the flue pipe and test up here.
It's already diluted.
It's already diluted because the air is coming in. We have to get to the top of the heat exchanger and test up there. So this one, if you put your hand up here and went up to the top, you can feel the tops of the heat exchangers. And this probe is long enough that it can get up inside here, and we can test inside right at the outlet of the heat exchanger. One thing you want to be careful of when you do this test is that it is hot inside here. You don't want to burn. You don't want to stick your hand too far in. That's why the probe is nice and long. This way you can actually get a good sampling without burning yourself.
All right.
Okay, so since this boiler is made out of cast iron, the heat exchanger, there's a lot of thermal mass in here. So when this boiler fires and we heat up this cast iron and the cycle is done and the house or the apartment is satisfied, we still have a lot of heat stored inside this cast iron. So what will happen is we'd have a little efficiency measure we put inside this. It's a flue damper that goes in the top, right, as the outlet of the heat exchanger. So what this will do is, if you look at the top, you can see a little damper in here and it's closed up. So when the system is off, to prevent off-cycle losses, this damper will close and it will stop that air from going in, getting heated up by the cast iron and working its way out. So you will cut down on those standby losses. This way we don't cool off that cast iron. So we have our analyzer here. We can stick it on the metal, so we have a nice magnet to keep it up and out of the way. And then on this pipe, we actually have a little hole drilled already for us. So we could just peel the tape off, and it exposes a little hole being drilled on there. When you do drill the hole for your test, you want to stay away from the 90s, because what happens is as the flue gases go through here, they turbulate a little bit, and you won't get a real accurate reading. So you want to be on a nice, either a horizontal or vertical section. At least 6 inches away from any 90, any bend in the flue pipe. So that's why we drilled it up here. So once we're ready to do the test, we'll fire the unit runs for a little bit. We want it to reach steady state. We want it to run for at least 10 minutes. We want it to run and make sure that everything is working properly, everything's heated up in the inside, the heat exchanger is nice and warm, the airflow is going across, and we can get a good average test of what's happening when the system's running. So we'll drill a hole and then we'll put our analyzer in. Analyzer goes in about halfway. We have a little depth gauge we can adjust to make sure that it gets and stays in there about halfway. And then what we can do is go ahead and turn on our analyzer. We'll hit the run hold button, which will turn on the pump. And now as the system's running, we start pulling flue gases in and we're analyzing them with the analyzer and testing to see what byproducts we have left over inside the, after the combustion process. On this boiler here, we have another different type than what we saw before. This one is actually category 4. So it's positive pressure in the flue pipe and it's also condensing. So this is a high efficiency boiler. If we take a look at the cover, open her up and look inside, we can see that we have 2 pipes coming in, right? So this little PVC pipe here coming in is our air for combustion. It comes in right from the outside, so this is direct vent. So we're pulling combustion air from the outside and we're also venting the flue gases outside as well. So the air is coming in down through this pipe and it gets into this compartment. Inside this compartment, we have a fan in the back, similar to the inducer motor we saw on the furnace. Same design, it's pulling air in and it's regulating the amount of combustion. So here's the inlet to that. So that air from the outside works its way into the compartment, gets into the inlet of the fan. As the fan pulls air through, we have a negative pressure gas valve inside here. And the way that's designed is the faster this fan spins, the more gas we pull in for combustion. So this one can actually modulate up and down to match the load. So if we need 100,000 BTUs, it'll give us 100,000. If we only need 20 one day, it'll give us 20 by adjusting the speed of the fan.
Much more efficient.
Much more efficient, yes. Having the ability to match that load, it makes the efficiency spike so much higher. Inside the heat exchanger here, we have about 2 gallons of water inside of this. It's a very small amount of water in this heat exchanger. So we need to continuously pump water through it to make sure that we don't overheat it. So with these type of systems, primary, secondary piping becomes very, very important. So having that water, that flow going through will keep our heat exchanger cool, making it work a lot better. The heat exchanger is a fire tube design. So we have water surrounding little tubes. These little tubes are where the flue gases go through and they exchange the heat to the water. As they exit on the bottom. They go out the bottom and they work their way up through this pipe inside here and connect to our PVC vent pipe. The condensation inside here, because we are condensing the flue gases into a liquid to get all the latent heat, is removed at the bottom. If you take a look down here, we can see this little trap at the bottom. So the condensation actually collects inside this little trap, works its way up, and then goes through our drain pipe into a little condensate neutralizer kit. This condensate is acidic, like we talked about before, so we have to have the proper venting. So it needs to be PVC or stainless steel, something that won't corrode. Being that it's acidic, we can't just dump it into the drains. You know, in New York City here, we have a lot of cast iron. So if we do dump it into the drains, we'll start to rot out that cast iron. So what we do is we actually send it through a neutralization kit, which is a simple little PVC pipe. It's a PVC pipe filled with lime chips, and that actually neutralizes the acidic condensate, and it goes in to the draining system as, you know, a non-acid. We just fired up the condensing boiler, and it's going through a cycle, and it's coming up to steady state efficiency. So we're able to do our combustion efficiency test of it now. So what I'm going to do first, being that the air is being pulled in from combustion right through here, we're pulling in room air, so we're going to seal it up. So I'm going to grab the cover, put that back on. But before I put it on, I'm going to run in my temperature probe because I can't use the temperature inside this room. I need to do the outdoor temperature. So I'm going to run this inside here so it samples the air that's coming in from the outdoors and we'll get an accurate reading. All right, so that's set up inside there. I'm going to grab the analyzer. We calibrated that outside, so we're set and ready to go. Put this on here so we can see what we're doing. And then on these systems, we have our combustion port at the top, so our testing port. So there's a little gray cap all the way up here. If we pull that off, now we have access into the piping without having to drill a hole. We can run that in, and we're also going to connect our K-type thermocouple to our air side to get our good delta, and we're going to run our analyzer. So the probe should be about halfway in, getting a good sampling of the gas going through, and then we'll wait a couple seconds. As we start to run the pump, you'll notice in a few seconds that you're going to see the oxygen level starting to drop. Now it's because, you know, the oxygen is being used in the combustion process and it's being converted into carbon dioxide, it's being converted into CO, hopefully not too much, and we're going to have some extra oxygen left over. But the majority of it's being turned into water vapor and carbon dioxide. So we went from 21% oxygen essentially down to around 3.4, and we're still dropping a little bit on dropping down. At the same time, we're also measuring our stack temperature. Right now, the delta T in the stack temperature is 103 degrees. So our net stack, the difference is from the outside, and the stack is 104 degrees right now. So much lower than a conventional atmospheric boiler. I mean, an atmospheric boiler that's running, we're getting about 300, 350, on a good day of a stack temperature. So this is much, much lower. Once we get below 135, that's when those flue gases start to condense and start to give up that latent heat. And then we have to deal with it.
Which is what we're looking for. That's the efficiency of this. Is
Right.
a lot of the heat that was taken up in water vapor is being recaptured.
Is being recaptured, right. And that's where we get our efficiency spike. Right now, we're running about almost 95% efficient. So the efficiency spikes on these are very, very high.
Now there's a lot of other numbers here.
So if you start from the top, we'll see our oxygen. Our oxygen left over is 2.2%. Our CO right now is 100 parts per million. So that's a little bit high for this boiler. I want to see that a little bit lower. So we do have to come in here and do a little more air adjustments on this and adjust that gas valve and try to bring that carbon monoxide level down a little bit. Our efficiency is about 92% right now. Our carbon dioxide is about 10.6%. Our stack temperature, 124. The air temperature of the air coming in from the outside is 68 degrees, because we have a little probe in here testing that. Our excess air is about 10.5%. So we don't have a lot of excess air. So the reason, being that we don't have a lot of excess air, we have a lot of carbon monoxide being produced. So this is telling me that there's either too much fuel or we don't have enough air getting into the combustion process. So I'm willing to bet with this system, we probably have a little too much fuel. The gas pressure set a little too high on this one. And then we're getting that air to fuel mixture is off a little bit. We're getting the carbon monoxide production. That's why we see a higher CO2 than we would want carbon dioxide, and we see a higher CO and a lower excess air.
So you really are fine-tuning these systems, even with something as brand new as this.
Right. You can't, expect that out of the box this is going to run perfect. I mean, these have been installed for a little while now, and they're relatively brand new, and you can't expect them to run perfect right from out of the box. There is going to be some fine-tuning to be done on that, and that needs to be recommended. A properly trained boiler mechanic needs to be able to go in there and set that up and make sure that burner's working at its optimum efficiency, because there's a lot of factors, a lot of variables that are out there that could change this combustion efficiency and these numbers.
Should every boiler technician that starts your furnace up every year?
They should be doing this, right? Things change. Components get dirty. There's a lot of dust, construction going on in homes, or if you have a dryer downstairs, a lot of times you get all that lint to get pulled into the burners, especially if they're atmospheric. So having a regular clean and tune, at least every 2 years. I mean, if not every year.
So from an owner's standpoint, or a building owner, or a building manager, when someone comes by to service your furnace or your boiler,
they should be doing this test, right? Just to make sure that this system is working as efficiently as it can. And there's no problems. You can find out a lot of problems with just these numbers right here on the analyzer.
Right. And just because someone sticks a probe in and hooks this up doesn't mean that they're actually reading anything. Right. You should understand these numbers. You
should understand what the numbers mean and why. And each manufacturer in their literature, in their owner's literature, have the numbers that they would recommend.
Right. Where are the adjustments?
The adjustments on these are at the gas valve on this one. So with this, we have the fan adjustment, which we can adjust the speed of the fan. And then we also have the amount of gas that can be pulled in. So right now the fan's running at a speed that it gets pulling air in, and then it's also pulling gas. If we choked back a little bit on the gas and brought less natural gas in for the process, our numbers would match up to where we want them to be. We would bring less fuel into the air that we have available, and we'll get a much cleaner combustion. So one of the things we want to make sure of when we do a combustion efficiency test on any oil-fired system is that we do a smoke test before we put the analyzer in the flue pipe. Reason being is that if we are burning poorly and we don't have complete combustion, with the oil system you can have carbon or soot deposits that actually go along with the flue gases and go out. And if they do get caught in the analyzer, you can ruin a very expensive piece of equipment. So taking the little smoke spot tester, we have a little pump, and what we have is filter paper. So inside this little packet here, there is some filter paper. We have a sheet here. And we can pull it out, and we can do multiple tests with this. So we break off a little piece, I'll give you this one. And what we can do is a little clamp. So this little nut adjusts, and we can open it up and we can insert the filter paper into the little slot, and we'll close it down. Now, one thing when you do this test, what you need to make sure of is that all this equipment comes up to temperature. Because a lot of times if this is out in the truck or the van or whatever you're using and it's cold on a cold day and you bring it in and then you just start to do the test, the first thing you do before warming this up, you're going to get condensation inside here. Because you're going to be pulling in hot flue gases into a cold metal pump, and they're going to condense and they're going to turn the water. And then you're going to have, this filter paper is going to be covered in water and it's not going to give you a good reading. So bring it inside, let it sit for a half hour. Most boiler rooms are very warm, so it'll come up to temperature pretty quick. So that's one thing I would recommend. The next thing is just to give it a few pumps just before you start. Pump it maybe 2, 3, 4 times just to clear out any dirt or debris that was in the nozzle prior. I mean, if you did a really sooty test before, there may be some debris left over and you don't want to compromise the reading. Actually, with the paper, I like to pull it through the paper. This way you collect the deposits and it's on there, and then I'll move it to another spot. And then I'll pull it over, I'll slide it, and then I'll set it up for another test just to clean it out, just to make sure that there's nothing left over that's going to compromise my reading. So what you'll do is that where you drill your hole, where you test, you're going to put the smoke tester inside. So what you're going to do is you're going to pull this 10 times. So you go 1, 2, 3, all the way to 10, just to get a good sampling and make sure that you're pulling enough flue gases through and making sure that it's going to get a good reading of it. When you're done, you have your 10th time, you're going to take the out, just make sure the tip is very warm so you don't hurt yourself, and you're going to open up the clamp and you're going to take a look at the spot. So we have a little spot on here, and it's not very clean, as you can see. So what we have inside the spot tester is we have a little scale that's provided with it. And we can match it up and we can get a number. And that number will correspond to how dirty the flue gases are, how much carbon is inside them. We want to see something that's less than 1. So in this case,
it looks like.
So this case, we match it up. We're probably right about 3. I would say 2.5, 3. So that means that it's a little bit on the dirty side. So we're not getting clean combustion
So
out
this is done before.
before we do the analyzer.
So what happens if I get a 9?
If you get a 9 or anything really high, you cannot test. It's going to clog up the analyzer. It's going to kill the pump.
The pump inside the analyzer.
The pump inside the analyzer, right. So it's going to get in. If it bypasses this filter, especially if you have a lot of it, it'll get past it. And some of the older models that didn't have this filter, you can really damage this piece of equipment.
Right.
The tubing inside here that connects to that pump is a very small diameter, 16th of an inch diameter tubing. So if you get any little bit of particles inside there, they'll build up and then they will cause the pump to fail or cause a blockage inside the
So what's
tubing.
the breaking point?
You want to see something less than a 2.
Less than a 2.
Right.
Okay, so even
2
this
or below.
is,
Even this, if it's a 3, I wouldn't test it.
now that we have these numbers, we can pass them off to the qualified professional.
Correct, yeah. What you'll do is once you're done, you'll give them the file and you'll say, here are the numbers that I got when I was out there. You need to adjust the burner. And they should know, based on what numbers you provided them from the efficiency test, what they need to do. Either they have to clean it out, adjust the air, adjust the fuel mixture, whatever it is. It's just, like I said, that air to fuel mixture needs to be correct. And their job is to correct it and then to provide you with the results that they have. So they should have an analyzer as well. And they should say, okay, we're done, we cleaned it out, we tuned it up, we got it running well, here's our results, and you go back and you can verify that.
And these have to be adjusted, these have to be calibrated.
Right, these sensors in here are field replaceable, which is nice. I mean, so you can call up the company, you can say, hey, I need 2 new sensors, and it actually give you the sensor life in the main menu of this program. So you go in there and see what the sensor life is, and if it's getting to about 50% to 40%, you want to call up and say, hey, listen, I need a few more sensors, and they'll send you out 2 new ones, and you'll be back up and running. You can just pull them out and pop them in. The older versions, you actually had to send it out to get calibrated. So you would FedEx it out to whoever, get them calibrated, they would come back, and then you'd be back in business. But they have to do the field calibrations for you.
All right. So that pretty much covers combustion analyzer.
Right.
Okay.
Pretty much.
Great, thanks.
Great. Hey, appreciate it.